Welcome to my fourth video in my series on energy, and today we're going to talk about work. And this is work in terms of the word physics, rather than just like work, going to work every day. So just same word, two different meanings. In physics, we have a very explicit definition of work. Work is the transfer of energy caused by a force acting through a displacement or a distance. Unlike force and displacement, which are vector quantities, meaning they have magnitude and direction. I have videos on vectors, all about them. Work is a scalar, meaning it's just a number. It doesn't have a magnitude or direction. So in terms of vectors, the work is equal to the dot product. And this is the force vector, and this is the displacement vector. And this is not a multiplication, this is a dot product. Like I said, I have some videos on that. If you're a little rusty and want to learn about the dot product, but it's not going to be totally necessary for this video to understand that fully. Now our force is going to be in newtons. That's the units on that. And this delta R vector, that is going to be the displacement. And when you move, you have a certain magnitude that how far you move in a certain direction. That's just going to have units of meters. So when we take the dot product of two vectors, we get a scalar. And so that's what we're talking about here. Now, remember on the dot product, A dot B is equal to the magnitude of A times the magnitude of B times cosine of the angle theta between them. So if we have two vectors right here, this is A, this is B, the dot product works out to be, that's the angle theta between them. This distance right here is going to be A cosine theta. So that's a projection of vector A onto B. So that allows us to write this equation that the work now is equal to the force times the displacement times the cosine of angle theta, where theta, well, let's just define all these. So work, W is work, and it's going to have units of joules, which is a Newton times a meter. That's our unit of work. Force, it's just going to have units of newtons. Displacement, that's just how far we move the object or system. That's going to be units of meters. And then theta is the angle between the force and displacement. So in this diagram here, this could be our displacement, and this could be our force, and that's the angle between them. So that tells you how the vector relationship breaks down into just a simple diagram here, and we'll use this most of the time in most of the basic problems. So what you want to notice here is that work and energy, because we've talked about energy, work and energy, have the same units. That would be in joules. The reason being here, work is one way of transferring energy. From one system to another. So work and energy are very closely related. They have the same units. And so when we do work, we essentially are transferring energy from one system to another. And we'll do an example of this and more examples just to get you familiar with this and how this all works. We're talking about work here. And we have three basic cases. The first one is going to be positive work. And this is for the angle theta less than 90 degrees. So in this case, the energy is transferred to the object. It just depends on these three cases, depending on if we're doing positive, negative, or zero work. And so in this case, it might be pulling a wagon. So if you're pulling a wagon, basically what you're doing is you're giving the wagon the kinetic energy. You're transferring energy from your physiological energy of your body to the wagon. And as the wagon moves, it gains kinetic energy. So that's the change in energy there. Also might be pushing a shopping cart. You're making the cart and whatever groceries are in there move, and that's adding kinetic energy, so that's a transfer. Now the trivial case is zero work. This is where the displacement is equal to zero, or the angle theta would be 90 degrees. An example with this would be like holding an object. Say you're just standing there, and for some reason you've got to hold this box right here, and it's kind of heavy. Now in reality, because you got gravity pulling down on it, and so it's going to be heavy. But in this case, you're actually not doing any work in the terms of a physics sense, because the box is not moving. The box, so delta R is equal to zero in this case, because you're not moving the box. So this is this case right here, holding an object. You're not really doing work in terms of physics. But now the same thing too is you're carrying the box across the floor, with the caveat the height is equal to a constant. In other words, you could be moving the object across the floor, but its gravitational potential is not changing. You are adding kinetic energy, but in the system where the work is straight down, like in the case of gravity, the angle is going to be zero between the force vector and the displacement vector. So that's going to give you zero on that, because the cosine of 90 degrees is zero. That one's a little bit kind of abstract, because you are moving the object, and you think, well, I am putting work into it, but you got to look at which direction the forces are. This is one case where you're looking at a very specific system and which direction the forces are moving or not moving. So that's can be a little bit confusing there. Now let's look at negative work. This is the case where 90 degrees less than theta, less than or equal to 180 degrees. So energy is transferred from the system. Remember, work is just a transfer of energy. So the force opposes displacement. Examples of this would be like friction. Friction is something we always have around us, and it opposes the change in direction. And then like when you put the brakes on a bike, you're opposing the energy is being transferred from the momentum or the kinetic energy of the bike into the heat going into the brakes to stop the bike. So that's one example of negative work. Now let's look at an example here. Do a simple numerical example. This is a classic example you see in every physics textbook. There's our ground. Here's our box. And in this case, the box is going to weigh 40 kilograms. And we've got a rope attached to this box. And we're pulling on it with 120 newtons. Now the angle with respect to the displacement, because the box is going to move from here to here, so the displacement is equal to 8 meters. and our angle theta is going to be equal to 30 degrees. So there's the case. We've got a 40 kilogram box. We're pulling it on a rope, but the rope is an angle of 30 degrees with respect to the horizontal, and we're moving it through 8 meters. So using our basic definition, or the definition of what work is force, distance, and then cosine of the angle theta. Theta is the angle between the work, the force, and the displacement in the direction of the displacement. So our force in this case is 120 newtons, and our displacement is 8 meters, and our angle is 30 degrees. And so you can see that's going to be Newton meters, so that's going to be Newton meters is our units, which is equal to a joule, so that's good. Now, let's put that in the calculator. Turn on my calculator, first of all. All right, so I'm going to just do this multiplication right here. I'm going to do 120 times 8, enter. That's 960. Now let's do the cosine of 30. So let's clear it. Now, cosine, we're going to do this in degrees. Now we need to check, and that's make sure that that right there is in degrees. The way we can change that is we go into the mode function, and you can see you can go down here to, okay, radians and degrees. So I'm going to just leave it there, and we're going to get out of the mode function because we don't need to change it. It already is in degrees. So that's what that tells us right there. So now let's do the cosine. .866. Now let's multiply that by 960. So that's going to be equal to 831 joules. So there's our answer. Well, I hope you learn a little bit about work here in the definition. In the next video, we're going to do an example, a couple more examples to get you more familiar with it. Well, thank you for watching, and if you have questions or comments, please leave them. I always appreciate hearing from you. Thank you.